All right, for this last example, we want to find the volume of the wedge sliced from the cylinder x squared plus y squared equals 1 by the planes z equals 1 minus x and z equals x minus 1. Okay, so first off, we know what a cylinder like this would look like. This actually is the classic cylinder that we know from geometry class, right? It's like a can. So we have x squared plus y squared equals 1, like this, and then we go straight down. Technically, it goes on forever and ever, but we're just going to give it a rest at that bit. And then we're going to cut into it. And you can see this with Maple if you want. You're cutting into it with two planes, right? With z equals 1 minus x, which is this green one here, and then z equals x minus 1 is that yellow one kind of right there. So they hit over here. So you have kind of one going up, and another one starts at that same point and goes down. And we're actually finding the volume in between the two. So z equals 1 minus x is up here. Right? That's z equals 1 minus x. And then down here on the bottom, we have z equals x minus 1. And of course, we're confined inside this cylinder, and we want the volume between the two, right? So there's the three-dimensional object we're trying to find the volume of, right? And this surface is x squared plus y squared equals 1. All right, so now what about the region of integration? Well, we want the xy plane. So if we think about the xy plane, inside that cylinder, but in the xy plane, would be a circle. Right? That's the region of integration. All right, so let's go draw that region. So this is the surface over here in 3 dimensions. Let's look at the region of integration. If we look at x squared plus y squared equals 1 on the z plane, or excuse me, on the z equals 0 plane, in other words, the xy plane, it'd be a circle. Right? We all know what x squared plus y squared equals 1 looks like. It's a circle. All right, so there's our region right there. Right? This is x squared plus y squared equals 1. Lovely. All right, so when we want the volume, right, we got to think about the pillars in here, right? So we'd be going from this low pink one to this top blue one. That would get us our height, right? So we're stacking pillars inside this object. So the volume is the double integral over the region of those pillars, right? The height of those pillars, which is take the top function minus the bottom function. Okay, so top in this case is the blue one, and the bottom one is the pink one, right? The pillar hits at the top at the blue one and the bottom at the pink one. Okay, so volume equals the double integral. We will have to figure out our limits of integration in a second. But the top function we know is 1 minus x minus the bottom function we know is x minus 1, and then dA. Now we have to choose which way we want to go over here, right? So in our region, do we want to go with a vertical or do we want to go with a horizontal? And the answer is it doesn't really make a big difference in this particular case. But generally, if it doesn't matter, then students tend to prefer dy dx. So this is dy dx. And the reason for that, I'm going to show you in just a second. Right, so if you don't have a care, then generally you go with dy dx. Now, why is that? Well, it's for the limits of integration. So we know this is a circle of radius 1, right? So we know this is -1 over here and this is +1 over here. Sorry, I have a stray marker there. 1 second. There, it bothered me. I had to put the numbers underneath. It felt wrong to have them up above. Okay, so -1 here, +1 here. Okay, so those are my limits for x. So -1, +1, no trouble. Now, the reason we like to do it with y first, then x, is that we're more used to solving for the top of this circle, right? The integral at the, or the function at the top and the function at the bottom. I have one more color of highlighter right here, purple, for y equals. because of algebra class. Because of algebra, we are more used to solving an equation like x squared plus y squared equals 1 for y. So that would mean that y squared equals 1 minus x squared. So y equals plus or minus the square root of 1 minus x squared. So the top here is the square root of 1 minus x squared. And the bottom is y equals the negative square root of 1 minus x squared. So that's the only reason. It's just that we are more comfortable from years of Algebra 1, Algebra 2, pre-calculus to solve for y equals than we are for x equals. And so if that's the case, then we choose y equals, because then we put the negative square root right here and the positive square root right here, and it's just more comfortable for us, not because it's actually any more difficult. Right? But comfort's important. All right, so now we just need to integrate this. But first, I'm actually going to simplify this. 1, take away x, take away another x, minus a minus 1 is plus 1. So this is really negative 1 to 1, negative square root of 1 minus x squared to positive square root of 1 minus x squared of 2 take away 2x dy dx. So then, that's the integral from negative 1 to 1 of the integral with respect to y of this is just 2 minus 2x times y. And we're going to take that from the negative square root of 1 minus x squared to the positive square root of 1 minus x squared. So then we plug in the square roots. So this is negative 1 to 1. 2 minus 2x just still sits there. And then we have the square root of 1 minus the x squared minus the negative square root of 1 minus x squared, which is actually 2 of those. So this whole thing becomes 2 times the integral from negative 1 to 1 of 2 minus 2x times the square root of 1 minus x squared. Right? I combine like terms, right? This is minus a minus, so it's plus. So there's 2 of them, so I put the 2 out in front, dx. And then I'm just going to go stick it into Maple and make it actually do the integral piece. And there's our answer. It's 2 pi. So I would say this is 2 pi. Oh, let's get it a unit. So let's pretend it was millimeters. I don't think I've used millimeters yet. So let's we're just going to throw this up here. Note x, y, z in millimeters, right? So if they were in millimeters and we just found the volume, it'd be millimeters cubed. Like that. All right, so that's the end of finding double integrals in rectangular coordinates. For our next section, we're going to come back and do it all again, but in polar coordinates.